בדיוק להתכוון אם זה גם לגבי הפרימיאלית, בקו שהראית, לדרייב לא היה לו כמעט חצי עם הנוסחאות וזה.
You're supposed to download the Word file into your computer and open it in Word. If you open it using the Google Drive, then that doesn't work well.
Okay.
And every now and again, I will save as PDF, and then the PDF always works.
Okay.
Yeah. Okay, so here we are again with calculus, and I'm thinking on where to stop as to the is called
Reminder.
no, it's not a good word. Like every class, I start with reminding you recap. Yes, great. Okay, with the recap. So I think that proposition, along with the drawing, is a good recap. Last session, we talked about supremum and infimum. A supremum is the lowest upper bound, right? Because the upper bounds of the set A, suppose that the set A is within these parentheses, the upper bounds are all here on the right, and the one closest to the set is the lowest, the minimal upper bound is called the supremum of the set. And then proposition said, what is an equivalent condition to being the lowest upper bound? So first of all, you must be an upper bound, obviously. But how can I say you're the lowest other than saying you're the lowest? We're saying something like this, which is very effective. If I take the number m and I move it to the left by subtracting some positive number and an arbitrary positive number, an arbitrary distance, we usually note by the letter epsilon. So given an arbitrary positive epsilon, if we subtract it from m, we will get a lower number than m minus epsilon, which is not supposed to be an upper bound, because m is the lowest upper bound. And how can I say that a number is not an upper bound if there's some element of the set which is strictly bigger than 8? And that's the proposition we've learned, and our first look at the idea of the epsilon notation. And then, as I said, it will get worse. But that was the first thing, and we proved that it's equivalent in both directions. And I wish to start today with an example. So assume or given two sets, two non-empty sets, A and B, of real numbers, such that A has a supremum and B has an infimum. Assume that for all A in A and for all B in B, A is always smaller than B. In simple terms, all of the elements of the set B are larger than all of the elements of the set A. If I would to draw these two sets on the line, on the axis, the set A would be to the left of the set B. Okay, so now prove the following. The supremum of A is not bigger than the infimum of B. So I'll start with a drawing that's not a proof, but it helps to understand what am I saying here. So the drawing would be as such. This is the x, well, it's too crooked. And this is the axis. So this will be the set A. And suppose the set G is quite close. This would be the set B. And the supremum of A would be here, right? Look, A. And the infimum of B would be here. Just a second. Move the screen up a bit. Supremum, the infimum, excuse me, the infimum of B would be here. And indeed, the supremum of A is to the left of the infimum of B. So now I'm pausing for a second and giving you a chance to think about it.
You just go on the stuff.
Yeah, it's like that, that's fine. Okay. So does that make sense? Now I see that you're seeing it a bit smaller than I would like. In the class full screen and hide video. Okay. So does this drawing make sense? Every element of A is smaller than every element of B. And therefore, I claim that the supremum of A is smaller or equal to the infimum of B. Does that make sense?
Yes.
It makes sense. And now, so it's one of the claims that propositions that make so much sense that students many times have a difficulty understanding what do I need to prove here? Isn't it what the netunim, what is given to me? So I wish to say that note, if supremum of A is within the A, what does it mean? Can someone tell me if the supremum is a member of the set? What does it mean? It's a maximum. Then it is a maximum. And if inf B is the minimum, then obviously by the data of the question, then obviously sup A is smaller than inf B, since every element of A is smaller or equal to every element of B. So in this case, like usual, if it's an attained limit, if it's within the set, if it's the actual edge, however you wish to call it, then the result is obvious because it's given by the data of the question. However, the interesting case is when it's not within the set. It's just like at the very edge, but not within the set, right? When the edge is fuzzy. I thought about it on my way here, and let's see if I'm able to do what I thought about. I'm opening Photoshop, not for too long. Don't get excited. That's a new file, whatever. And I'll take the brush here. Great, yes. And now I can choose which brush I use and the hardness. You don't see anything, it's too small. Oof. And let's look for Google. And brush, Photoshop, hardness. That would be nice. Okay, I'll take this one. So, copy image. So what is my point here? The maximum having a maximum is like the hard brush is like the hard brush, whereas having only supramoon is like the soft, fuzzy brush. You see my point here?
Is the maximum given, it's like a hard border?
Yeah, because it's like a point that existed. It's not the fact that the center is harder doesn't really matter to me. But I can point and say, this is the edge, this is the end of the brush. But here on the fuzzy one, it's very hard to say what exactly is the edge of the brush. Do you agree? And so if I say all of the points on the brush, on the harder brush, are to the left of the points of another harder brush, then obviously the edge is different. But think about two fuzzy brushes. And I wish to say the edge of this left fuzzy brush is smaller than the right fuzzy brush, but fuzzy brush. And I think this visualization explains why is it harder to work with such fuzzy brushes, and why all the epsilon there and the hard mathematics is because we are dealing with a hard situation. Okay. So that's not math, right? It's just visualization, but I hope it helps a bit. So now let's go to the actual proof of the proposition. Proof. So ABC, I like that. Assume by contradiction. I will remind you of that. Contradiction. That the infimum of B is actually smaller, strictly smaller than the supremum of A. Exactly. Okay. So proofs by contradiction are usually more often than not, hard to visualize because they contradict the data we are given. So if we look at a drawing, how can I say the infimum B is to the left of the supremum of A? That doesn't make sense. Yes, it doesn't make sense because it's false, right? But still, it's a very effective method of proof. So we assume that the infimum of B is smaller than the supremum of A. Take the middle number between the two numbers above, what is the mathematical term for the, not term, formula for the middle part?
Of A, infimum of B divided.
Yeah, there is sum divided by 2, exactly. So the infimum of B, sorry, is smaller than the middle, which is infimum of B plus supremum of A over 2, which is smaller than the supremum of A. Now, what makes me think about the middle section, I will draw it for you to understand.
I mean, this is mostly related to the element, like, we were talking before how if there's a supremum and we want to demonstrate there is, like, you try to contradict and say there's not, then there should be an element between
You
the.
are correct, Omar. You are correct. And I'm drawing it, but it's exactly as you said. The middle part, well, it's not exactly middle. The middle part is here. That's the inch B plus 2A over 2. Okay? So what am I saying here? This is the supremum of A, meaning it's the leftmost, it's strictly closest to the set, right? The middle part is smaller than that. What would we call this distance in the proposition in the recap? No, the distance is the epsilon, right? So I won't mention epsilon in this proof. I could, but it's a waste of time because I understand where I got to, right? But if I take an epsilon step backward, I will get here. Is this an upper bound of A? This is the lowest upper bound of A. So any smaller number is not an upper bound of A. What does it mean? There is an element of A here. And again here. So what I'm actually creating is some fuzzy point of the fuzzy brush here and some fuzzy point of the other fuzzy brush here, but then we have a whole intersection. It contradicts that every point of the fuzzy brush here should be to the right of every point of the fuzzy brush here. So I'll write it in a second, but again, the infimum of B is the maximal lower bound, which means this is not a lower bound anymore, which means there's some element of B here. I will draw these elements. So here I expect to find a B, and here I expect to find an A, and now I found actual elements of the sets which contradicts the data of the question that every element of A is supposed to be smaller than every element of B. And now I found an element of B, a fuzzy element, and which is smaller than a fuzzy element of A, right? And the reason is, again, for the last time, supremum and the infimum are not elements of the fuzzy brush, they are the very edge, but there has to be fuzzy elements close to them. Okay, and that's what happens here. So that's the explanation of the mathematics. The mathematics is what I'm going to write. I said it within my explanation, but fuzzy brush is not a valid proof. So what I did say is, since the middle part is smaller than supremum of A, and sup of A is the least upper bound of A, then the middle, I wish to give it a name because copying the whole formula each time is silly. So let's call it M for middle, no, that's D for middle. Okay, so just a second, I will put in my drawing as well. So here, that makes everything much nicer. Okay, so that's the middle part, D. So since D, the middle part is smaller than sup A, and sup A is the least upper bound, then D is not an upper bound of the set A. And what does it mean that it is not an upper bound? Therefore,
There's something below.
yeah, there exists A in A such that A is larger, it's not below thing, but it's above.
But we're not saying it's infinite.
It doesn't have to be.
If the number isn't the upper bound or lower bound of the
It
set.
doesn't have to be an infinite amount because the set doesn't have to be infinite. It doesn't matter. One is enough, right? It's not an upper bound, some element is above it. Okay. Similarly, there exists and B in B such that B is smaller than D, since D is larger than the infimum of B, and B is not a lower boundary. Lower bound of B. Finally, set A is set B is smaller than B, and set A is larger than B. In contradiction, we found elements such that B is smaller than A, but we said A is always smaller or equal to B. Any questions? Any questions so far?
I'm thinking, so the only situation where this becomes confusing is when the infimum of B and the supremum of A are equal, right?
Yeah, but it's not confusing because the very element are the maximum and minimum themselves. We did such an exercise last time, and we proved that if there is a minimum, that it's also an infimum, right? Because the element that is lower than, or I'm not sure on which maximum. So the element that is bigger than m minus epsilon is the maximum, the very maximum itself. So in this case, the so-called D is the very element which is in the intersection of the two sets, the maximum small one and the minimum of the upper one. So there is no problem with this proof. It works always. But in the case there is a maximum and minimum, you don't need the proposition. It's obvious, like I said in the note. The fuzzy case is the more interesting one. And again, other than learning about boundaries, we are starting to get the notion of limits, which is the basic language of this course. And in that notion, we will go to the next example, interesting example. Assume given a non-empty set A of real numbers of real numbers does there has to be supremum of A. Does every set have a supremum value? What do you think?
No,
Why not?
because there are infinite sets that, for example, the natural numbers. For every
Yes.
number, there's a bigger number.
The second thing you said is wrong, because the fact that for every number there is a bigger number, that's the fuzziness, which does not preclude having a boundary. But the natural numbers is a good example because it doesn't have an upper bound. No, the set could be unbounded, such as not uncounted, unbounded, such as A equals, and I'll go with your example, the natural numbers. Right? There is no upper bound to the natural numbers, not to say least upper bound, because there is no upper bound, right? The supremum is the least upper bound, the smallest upper bound. If there are no upper bounds, there is definitely not one which is the least. Agreed? But what happens if there is some upper bound? Say now that the non-empty set A has some, at least one, upper bound. When it has one, it has an infinite number because every larger number is also an upper bound. But say A has at least some upper bound, it's bounded. Does it have to have a supremum?
Yeah,
Why?
well, because you already said it in your explanation of the question, there's infinite upper bound, but.
So what? Who says there is a least one?
No, because through these upper bounds, the quantity is immeasurable, the
So-
one must be the smallest one, you know?
No, and the answer is yes, but not because what you say. It's a bit delicate, and I would say the following: in the set of rational numbers,
Yeah, that's the caveat.
the answer would be no. If we take B to be a set of all rational numbers such that x squared is smaller than 2. The least upper bound is the square root of 2, which is, like we said, a real number, right? If in a world where the numbers are only from, excuse me, are only from the set of rational numbers, I'm saying, why do we need the rational numbers here? So if no one has invented the real numbers, sorry. If no one has invented the real numbers and there were only the rational numbers, there is no minimal upper bound, minimal upper bound for the set B. Because there's always another rational number which is a bit closer to the square root of 2, since the square root of 2 is not a rational number. And I have to say, this is not a valid proof, just an explanation, okay? I won't do a valid proof because we wish to go in other directions, but I need to prove that every rational number which bounds this set from above, one can choose a smaller upper bound, smaller rational number, which is in fact closer to the real so-called square root of 2.
You just keep doing that essentially.
I don't have to do it twice, right? Because that's the
Do it
proof
once,
that there is
yeah.
no minimal one. If there was a minimal one, I get a contradiction. But yeah, and that's the fuzziness again. The rational numbers are fuzzy. They don't have the hardness of the real number, which includes the square root of 2, for example. So this example is one of infinite number of examples, but one is enough. Okay, so again, it's an explanation, the second one in this course, for why do we need the real numbers. And it's essentially the same because the other one which I gave to you with the bicyclist and the train, and the mathematical proof that one of one, I'll go back to remind you for a second. Wait, after that. I didn't give you that, so. Did I prove the square root of 2 is not rational?
Yeah.
Where? That's why I'm not seeing it.
I think it was like pretty much.
Oh, it was before, yeah, it was before. Okay, so this was the bicyclist and the train. So. There is a bit of a lag. I'm not a magician, I already scrolled ahead. Just a second. There's a lot of lag. Yes, okay. So, the claim that the graph of the function x squared minus 2 goes from this point to this point and therefore intersect with the x-axis, and the proof of this, the theorem behind it, the mean value theorem, uses the fact that I will say in a few seconds that each bounded set, non-empty bounded set, has a supergroup. So it's essentially the same idea given in different notions, and we will see later how they connect together. But again, I'm speaking about why do we need the real numbers, which are much more complicated than just the rational numbers. The rational numbers, some sets, bounded sets, does not have an edge, does not have a supermoon or an infimum. It's very hard to do calculus in this way. Question?
The same way that 0.99999 can be represented by 1.
It's
Can you have a representation like that for irrational numbers?
or irrational number, of course. That's the decimal system. If I write square root of 2, saying Wolfram alpha, I would say Wolfram is say square root of 2, and that's that. So if you mean here, if you mean does the digits have to be in some sort of periodically? The answer is no. Every number, every decimal number that ends with a periodical continuous of the same string going back again and again is a rational number. So every irrational number has some sort of
If technically 0.999 is a rational number, so. Okay, fine.
it is a rational number, right?
It is.
It's a periodical, 999, it's the same ending going over and over, it's a rational number because it's one, right? So square root of 2 have some representation by digits, but it's not
So you can't-
periodical
You can't say
one.
that this number is the super.
Not in the rational, yeah, because it's not a rational number. Right? It's not a quotient of two integer numbers.
Technically, this is a rational number.
No, but it's not the whole square root of 2.
Yes, so it can't.
It's not the end, right? There is no end. It's an infinite series of digits. Yeah. Yes. Okay. Number name 1.41. That's silly. Okay. Yes. So facts which I won't begin to prove, facts in the real numbers, every non-empty set with an upper bound as a supremum. In the rational number, it's false. In the real numbers, it's true. We will use it in order to so-called prove it. We have to actually define the real numbers, which is a lot of work. And whoever wants to read about it, read about Dedekind cuts. But for our course, we just assume that it is true.
And we use this back then.
Yeah, and we will. Don't just you yourself won't use it because we will use it in the proving of some theorem. You use the theorem, it's not this fact straight, but yeah, we will use it. And just to understand why it's true without proof, it's because you can continue the decimal number to infinity and then make it as accurate as you want. As the supremum is the decimal number with the infinite series of digits, sequence of digits. So that's the main idea behind it.
If it's an infinite sequence of digits, then you're always gonna have something right after it.
No, because if it is the infinite sequence, then it's one number and you can't be more close because you took all of the infinite digits, right? You're at the very end. But that's not a proof. It's hard to understand because it's not a good proof. It's not good proof. And the real proof, as I said, it's much harder because you have to define the real numbers, and we did it. The very idea of a number with infinite sequence of digits, it's hard to accept, rightfully so. Okay. Any questions so far? Okay. So our first chapter is then ended. We talked about numbers and we talked about boundaries, upper bound, lower bound, supremum, infimum. And now we will start to discuss limits of sequence.
Oh, we're not gonna prove the last question.
The what?
We're not gonna prove the answer.
For what?
The go
For this question, that's the fact. That's the fact, that's the answer. And I said, no, we won't prove. Take a few good lessons and also knowledge of discrete mathematics, because that's the way we define the real numbers using bounded sets of rational numbers. But we don't do it here. Okay. And general thing, when in Hebrew we say sidra, many times people would translate it as series. That's what we do on Netflix. But in mathematics, a series is a sum, an infinite sum of numbers, tool, which we'll also discuss. And the sidra of numbers is called a sequence. Okay? And so we wish to discuss limits of sequences. And I'll start with the following few examples. Given examples, and I remind you, I always do some introduction before I give the actual mathematical definitions. Hard to some R missing here. Look at the sequence an equals 1 over n. What is that sequence? What are the elements of said sequence? So an is built from the first element is 1, and then the next element is half, and then 1/3, and then a quarter, and so forth. Do you agree? If I would ask you, what do you think the limit of this sequence is, what will you say? 0, you will be right. Look at the sequence. The constant sequence 1, whose elements are 1, 1, 1, and so forth. What would you say? Would you say the limit of this sequence is?
1.
1. This is the hard case rather than the fuzzy one, right? It's the we have a maximum and minimum and all the good things, right? The sequence is constant, right? Doesn't really, it's not really interesting. Next, let's look at the sequence Cn, which is minus n to the power of n, minus 1, excuse me, to the power of n, whose numbers are negative 1, 1, minus 1, 1, and so forth. What would you say the limit of this sequence is? Yes,
There is no.
there is no limit. There is no limit. Very great. Is Cn is the set Cn bounded? Yes, right. The elements are only 1 and negative 1. It's bounded in the minimal number minus 1. The minimum is minus 1, and the maximum is 1. So it is a bounded set. I wish to elaborate on that. Is the set of elements of the sequence Cn bounded, right? Cn is the sequence, an ordering of numbers, but if I take the set of elements, it's just the pair negative 1, 1, which are the minimum value and maximum value. Yet there is no limit, yet there exists no limit to the sequence. And what I'm saying here is, you see why is there a difference between boundaries and sequences, right? The sequence has boundaries, a supremum, an infimum, maximum, minimum, but it does not have any limits. And we need to understand what is limit. Any questions so far? So you see that intuitively you understand the idea of limits. I gave you 3 sequences, you got the limits correctly in each and every example, but it's still hard to give a mathematical correct definition of why did you say the limit here is 0, the limit here is 1, and there is no limit here. And what will we do for the next few minutes is try together to give a definition. At first we will fail, and the purpose is to explain to you why is the definition so convoluted rather than simple, because it doesn't seem right that we understand it intuitively so fast, but yet the actual definition is not easy. But I'll try to convince you that it has to be a bit more convoluted, like I said. So why would you say the sequence 1/n tends to 0? Right, this is the first sequence an. You said its limit is 0, and I asked of you, why would you say the limit is 0? Yes.
Because
That was weird.
I was literally about to start and I was like, no, it's.
Yeah.
Every complete fraction is bigger than 0.
So first of all, in layman's terms, in mathematical terms, 0 is a lower bound. That's what you actually said. First, 0 is a lower bound of the set of elements. But what about the sequence minus 1/n? What would you say its limit is?
0.
Also 0. And now it is the upper bound. It's supposed to be the, I don't know, the opposite of limit, but it's still a limit, right? Yes.
It doesn't have a period.
It-
There's no periodicity.
Periodicity.
Periodicity to the sequence. There's no repeating set of numbers.
So what? Why is 0 the limit?
No,
You have to
well,
say something to do with 0.
and specifically with 0.
Because 0 is the limit, right? There is one limit, you all agreed it's 0. You have to explain to me, how did you know that? How did you know that 0 is the limit and not any other number or number?
Because the numbers are decreasing.
So it's a lower bound, right? It has to do with it could be with the decreasing and increasing. I will give you a counterexample in a few minutes.
Why
but-
is it like minus
Yeah.
1?
Yeah,
I mean, saying tends to infinity is a bit skipping ahead, I think, but the bigger the n, the smaller the number, but even as I said.
that's again calling it a lower bound.
Yeah, but
Decreasing.
yeah, but like both things put together, given that every positive fraction is bigger than 0, and given that the bigger the n, the smaller the number, then it must tend to 0.
Why not -1? It
Uh,
also tends to -1.
why? Because it's the biggest.
So
It's the smallest number that.
given a decreasing sequence, it is true that the limit would be the infinite.
Oh,
That's true. And in increasing,
that has something to do with convergence and divergence.
yeah, having a finite, number as a limit is called convergence. So, however, what about non-decreasing sequences?
non-zero.
So you are correct in saying that when the sequence is decreasing, it would make sense to define the limit as the infimum, and then when the set is increasing, I will define the limit as a supermove. And it will go nicely with the ideas we learned so far. That's why we learned that. But look at the following sequence, let's call it df, which is -1 to the power of n over n. Look at the elements here. And it starts with -1, then half, then minus third, then a quarter, and so forth. The boundaries
Are one times one.
of these set of elements are -1 and half,
Yeah,
right? The largest is half, the least is -1, yet the limit,
zero.
yet the limit is still 0. So boundaries does not help, and it's not nothing, but it's not enough to cover every sequence, sadly. It covers perfectly increasing and decreasing sequences, as we will learn and prove later in the course, after we'll define limits correctly. But it doesn't handle the general case, sadly. And I wish to remind you the graph. I have already shown you such a graph, but I'll do it again. Look at sine of x over x in order to be nicer, sine of e to the x over x. Oh, yes. Look at this beautiful graph on functions. What would you say the limit of this function is? It's not a sequence yet, but it's basically the continuous version of this sequence, right?
I think, I mean, I don't know.
What is the limit?
Zero.
It's 0, right? First of all, let's agree on that, because the function tends to 0. It's non-decreasing, not decreasing, non-decreasing, and non-decreasing, but still the limit is 0. Tomas, yes, you want to say something?
I think maybe we can explain by saying, in this case, there exists for all epsilon, if you add it to 0, then there's a number that's big, let's say smaller, and if you subtract it from 0, then there's a number that's bigger.
It's close, not exactly. I don't have to be on two sides, but there is something like that. Yes.
I was gonna say, is it possible to define it as a limit is a value that the sequence, every next number in a sequence will get closer to that value or equal to it.
So you think about the absolute value of the sequence and say, okay, it may be above the x's and below, but the absolute value. So with the function, you see it's false. In the sequence, it's harder to show you, because in the sequence, the absolute values were 1, half, and third, and it was actually closer to 0, as you say. But in the function, it's not. See, this number is further from 0 than this number, so we got closer. But this number is again further. So I go back and forth.
Yeah, because in the sequence you're using the natural number.
Yeah. So, but I can do a similar thing with a sequence. Another example. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120 I won't even bother with the formula. Say 1, then 2, then half, oops, then half, then 1, then a quarter, then half, then 1/8, then a quarter. So in order for you to understand the formula in my head, I started doing with 1 and 2, and then each time I take half of the, not the last number, but the one before it, right? So it's 1, half, a quarter, an eighth, and so forth. And here it's 2, 1, half, a quarter, and so forth. So this number goes up, and this sequence, sorry, goes up and down, but still tends to 0. So it doesn't have to go straight to 0. It can fluctuate, but the fluctuations are smaller, right? It is closer to 0 in general, but it's hard to define exactly how. And that's what I wanted, I always do this discussion in order to understand the limit is a bit more complex than just boundaries. It's obvious to us that these go to 0, but it's very not obvious to explain why. How come we know it? Agree? So now I'll give you a hint in the right direction. Question. And then also a recap. Given an area of the number 0 of size 1, i.e. the segment between -1 and 1. You remember the idea of an area? We have a number in the center, and then we go up until some radius to the right and up until some radius distance to the left. So the segment between -1 and 1 is an area of the number 0 with the radius 1. Is it true?
Just to be sure, this
Yeah.
is from x minus 1 to x1, not y. Like,
Yeah, it's on the x-axis. Later it will also be in the y-axis, but for now it's on the x-axis. Sequences doesn't really show in the graph anyway, so it doesn't really matter, right? But it's a set of numbers between -1 and 1. The center is 0 and some distance on both sides. Is it true? And I'll change it up. Excuse me. Size 2. Just for the first element. Is it true that all of the elements of this the sequence 1/n are included in that area?
now what do you mean by elements from 1 to?
But 1/n are all numbers of the sequence 1/n. At the very first sequence we started to talk about, this one, are all of them within the set of numbers between -2 and 2.
Yeah.
Obviously, right? And I'll show you in GeoGebra why I'm even asking that. And clear all. Let's take the center 0, and the distance would be 2. And then we take 0 minus d, 0, and 0 minus d, 0, 0, 0, nothing, that's 0 plus d, 0. So these are the edges. These are the edges of the area.
Here's where you subject directly to perfect.
Hmm? And it's just sequence. Just a second, expression variable. Okay, so sequence 1 over n, where n from 1 to 100. Okay, let's multiply 1, excuse me for a second. 1 over n 0, 6, and 6, 1, 600. Oh, great. Okay. So I draw the first 100 elements of the sequence. Are they all between -2 and 2? Yes, they are all within. And would you expect them to be there? And I would say yes. Why? Because you said, we think 0 is the limit. So if we take some area around 0, we expect the sequence to be there because it tends to 0. Agreed? Now, what will I do with the d? It's called d here, distance, radius, we'll call it epsilon later. What should I do with it next?
It's smaller.
Make it smaller. So let's make the distance smaller. As such. Is it true now that's 1/5, the area of 1/5? So I'll write it up and then I will ask again. Now, next, look at the area around 0 of radius 5, i.e. the segment between what and what?
-1/5 and 1.
Yeah, -5th and 5th, right? Because it's 0, it's quite easy. And in the following drawing, illustrated in the following drawing, right? Are all the elements of the sequence contained within this segment?
Obviously not.
No. But it still doesn't change your mind about this being the limit, right? You still agree that the limit of the sequence is 0, even though not all elements are within the area. Why? How would you describe the connection between the elements of the sequence and said area? They are not all within it, but what is it true to say?
They're all going into it.
But they're all good. A certain number goes nowhere, right? This number, the first number of the sequence, is not going there, it's out. But how?
Sequences.
Yeah, but why? How? Let's just say how many of the elements are within the area?
Most, majority.
Yeah, so actually your answer was better in this case. Because you say majority. What would happen if some, let's look at the, okay, I'll write a few things and then I will challenge you with the next challenge. Here, not all elements are within the area, but most are, or all but 5. Okay, both descriptions are true, but one of them is more important to me, and I will explain why. Look at the sequence -1 over n in the power of n over not the total alignment, sorry. Look at the sequence -1 to the power of n. How many elements are within the area of 1 and the 0, 1, 0, 2? Okay, do you agree this is an area of the number 1? How many elements of this sequence are in this area? No?
Sequence.
-1.
Sorry, half.
So half is like an infinite so-called half are in and half are out. It's not actually a half because it's an infinite number, right? It's infinite of half. And it doesn't matter what it's half, it's an infinite number. An infinite number of elements are within said area, and an infinite number of elements are out. Would you say that 1 is the limit of this sequence? No, we saw the sequence before, right? We saw it's -1, 1, -1, 1, and it has no limit. Certainly, we wouldn't say that the limit is 1, right? Why don't we say the limit of 1? What is the problem here? How many elements are without of the area? How many elements of the sequence -1 to the power of n are not in the area 0 to 2? An infinite number. But here, how many elements are out of the area?
4.
It's 5 actually, because it's not included in fifth, but it's a finite number. So all but a finite number should be in. That's what we wish to have happen. And if we decrease d even more, say, slider increment of 0.01, and the beta amount would be 0. So if we decrease the even further, that was too much, sorry. Here. Just a second, slider. So if I decrease the size of the area even more to 0.004, how many elements are within the area? Infinite number. That alone is not enough. How many elements are excluded?
Finite.
A finite amount. Okay, and that's the main point. And it doesn't matter how large is the radius, how large is the area, what is the resolution. It's all about resolution. If we zoom in, we see that many elements may be out, but from a certain index, all of the elements are within the area. And it doesn't matter how much we zoom in. By the way, here it looks a bit problematic. Why are there no elements here?
They can't calculate it.
Because I drew only the first 100 elements of the sequence. But if I was able to draw infinite number of elements of the sequence, it will continue. And it doesn't matter how much will I zoom in, how much will I improve the resolution, the sequence will always be in the area of 0. What does it mean? All but a finite amount. And a finite amount, and we compare to the infinite number of the elements in the sequence is always negligible. That's the idea behind limit. And thus, we don't care if it's decreasing, increasing. Let's just see for a second. I'll take a couple of more screenshots.
So that's what you meant when you said that what I was saying was close when I said epsilon bigger or smaller, just the epsilon in this case is the radius.
Yes, but I need for all epsilon, and I need for all but a finite amount of elements would be inside.
Okay.
So that's the very definition of the limit. We'll write it up in a few minutes. But that's the idea. Yeah. Wait a second, I copied it. Whoa. Okay, and it does not matter if the series sequence, or if the sequence is increasing or decreasing or such. And look at the following example. Change the sequence to be -1 to the power of n. So here, and let's continue it until 1,000. Okay. So here, you see elements of the sequence starting with, where's -1? Oh, well, it's 4. Okay. So here you see the resolution. So the first element of the sequence is -1 to the power of n over n, meaning -1, then half, then -1/3, yes, then a quarter, then -5, a fifth, and so forth. And it goes back and forth, right? Non-decreasing, non-increasing, not both. However, if I take, I'll take a screenshot of that first. And look at -1 to the power of n. But when I zoom in, when I look at an area of 0, certain area of 0, can I say all of the elements of the sequence are within this area? When we look at a small area of 0, are all elements of the sequence within this area? No, right? Not all elements of the sequence are within the area, but what can we say? No, but that's the fact that it's an infinite number is not enough. Like I said, because there could be all but a finite number. But all, I don't want to say but twice. However, however, all but a finite amount. And does it matter how much did I zoomed in? How small is the radius? No, it doesn't change the answer. Okay, that is true for every radius of an area of 0. So basically, the idea of limits, is that no matter how much we zoom in and improve the resolution, always all but a finite amount of numbers of elements of the sequence are there. I will write it pretty short, sorry. I wrote a lot. So I will write it in a few seconds as a mathematical definition, but it's basically this. I wish to say for every area of the so-called limits, all of the elements are there, but a finite amount that is allowed to stay out there, out of the area. And now I don't have any problem with boundaries, with increasing, and just saying I look at an area of the limit and the sequence is just there. It doesn't matter if I look closely or not, it will be there and not anywhere else. I'll give you a minute to copy it. And then I will write up the formal definition. I will write up 2 formal equivalent definitions, one using the more words, the area idea, and then using the epsilon notation, which is helpful for proofs later on. Okay. We are ready. But a finite amount, more or less, for the formal definition. Given a sequence and a number L, a real number L, which is supposed to be the limit, we say that the limit of an is L, or an tends to L, these are 2 different ways to say the same thing I'm about to define. We either say that the sequence tends to L, or the limit of the sequence is equal to L, if for every area of L of an arbitrary size, big and small, it doesn't matter, all of the elements of the sequence AN, but excluding maybe a finite amount are contained within the said area. Okay, it's a formal definition, it's not verbal, right? I will have one with the epsilon in a few, but for the idea of a limit, I think this is easier to understand. Why is that the definition of a limit? If I take any area, any resolution around the limit, the sequence will be there. How much of the sequence? All but a finite amount. The finite amount could be huge, it could be million, billion to the power of billions elements out, but still, from a certain index, from a certain index forward, all elements are within the area. I'll put it in parentheses. That's an explanation, right? But that's what it means that the finite number is out. After a while, we get the less number that is out, and from now on, in perpetuity, everything is in. So now we will write up. Now we will write this definition in an algebraic form, version, notion, whatever. So AN tends to L if for every, so what measures an area? What is the difference between one area and another area of the same number L?
Radius.
The radius, right? So for every radius, and how do we, what is the name we chose for radiuses? Radii?
Oh, no, sorry.
No, it was in the example, but in general in calculus, what is the special letter?
Epsilon.
Epsilon. Right? It could be D just as well, right? Why does it not like right now? Okay. So for every radius, I wish to say that from a certain index forward, everything is within. So I would say there exists an index K there exists an index K such that for all indices after K, it is true that. Can any of you complete the sentence, right?
AM is inside of the radius.
Yes, so, correct. So what do I write? There are two ways to go about it, but I'll write AN is in the area. What is the area? What is the left side of the area? L minus epsilon, and the right side of the area? L plus epsilon, perfect. That's the definition of a limit. Okay, and note, and this algebraic notation is equivalent. No, it's equivalent if and only if the distance between AN and L is less than epsilon. Do you agree? Right? Saying that AN is within L minus epsilon and L plus epsilon is the same as saying that the distance between AN and L is no more than an epsilon. Sometimes we use this equation, and sometimes we use this form of an equation. I will use both during class. So you need to convince yourselves that these are actually equivalent claims, algebraic claims.
If A is negative and you do -7, wouldn't it be more negative? Like, no, I mean, because like.
Yes, but it's all, yeah. If we take any number on the axis, if we subtract a positive number, we go to the left. It doesn't matter if it's positive or negative. It works. Okay? We do have to make sure that the epsilon, the distance itself, is a positive number. Otherwise, we get nonsense, right? But yeah, that's why we always say let there be a positive epsilon. We start with that. So epsilon is not a number. It's just the letter of the radius, right? And our demand is the thing that I don't think that the idea will work for every positive epsilon, every resolution. Obviously, when epsilon is smaller, it becomes more problematic because you zoom in way further, but it has to work always for every resolution, from far as from close within. Agreed? Now for some post drama from discrete mathematics, and then we'll finish, sorry, in discrete mathematics form. It's quite easy. Look, for all positive epsilon, there exists a natural K such that for all n larger than K, A and minus L is smaller than epsilon. So it's the very same definition, just written in logic terms, which we learn in discrete mathematics. But this small proposition or pasuk, like I said in logics, that means that's the definition of a limit. And why is it so hard? Because it has three quantifiers, three interchanging quantifiers. For all, there exists for all. That's what makes it a hard mathematical concept, but we will work with it for a while, and that's enough for today. And see you in today. It's going to say fail index here. It's possibly like the A1, the index is 1, A3, the index is 3, and it's called an index.
Oh, it's
like a place within the sequence.
In the sequence. Oh, it's just like it's some number within the sequence.
But the index is not the number, it's just the place, right? So 10 number could be 30. So the index is 10.
Index is 10, but the alpha, it could be the
Yeah.
Okay.
The index is the serial number.
Okay.
No way.
אבל הנה, for every radius epsilon there exists an index k such that for all n larger than k, it's true that
an is the element of the open interval L minus epsilon. Okay. הוא מאבד אותי עכשיו.
כן, לא. היא בשוק, הסימטר כבר התחיל, איך זה לא אבי?
מבחינתה, אני מלמד את כל ההרצאות, ומבחינתה היא תיכנס לגיאומטריה, היא תראה אותי שם.
כן, כן.
את החומר אני לא יודע. זה מה שאני רואה. פתאום, קיימתי את זה, כן.